In the last section of Chapter 5, which is 5.4, we're going to look at sampling distributions and the central limit theorem. To motivate some of the definitions and to show you how this is going to work, let's consider the population of HTTC students. We could go ahead and gather the GPA of every single HTTC student, add them all together, divide by the total number of HTTC students, and let's suppose that we get that population mean is 2.96. Not difficult to do. Again, there's a fair number of students at our college, but instead of doing this, let's just suppose we do the following thing. Let's create all of the different possible samples of size 3 from this population. So we're going to pick one sample of size 3. Let's call this the set S1. And suppose these are the GPAs of 3 students. There was a 3.01, 1.97, and a 2.41. If you take these 3 numbers, add them all up and divide by 3, we would find that this sample mean, let's call it x1 bar, would be equal to 2.46. Let's now go ahead and take a different sample of size 3. Let's call this S2. Suppose these 3 students had a GPA of 3.89, 2.91, 3.01, etc. You would again add them all up, divide by 3, and we would find that that sample mean, x bar 2, would be equal to 3.27. We can continue to do this over and over again, and we'll repeat this procedure until we find the sample means for all of the different possible subsets of size 3. So we have a brand new distribution. Let's collect all of those sample means. These sample means are going to become part of what we call our sampling distribution. This brand new distribution, which is the collection of sample means, will itself have a mean, which we're going to call mu sub x bar. This is the mean of the sample means. You will often hear me refer to this as the mean of the sampling distribution. And it too will have a standard deviation, which we'll denote by sigma sub x bar. And this is called the standard deviation of the sample means. You'll oftentimes hear me refer to it as the standard deviation of the sampling distribution. It's also, there's a common synonym for this as well. It's always also sometimes referred to as the standard error of the mean. If you're curious as to what the size of this sampling distribution would be, even though we don't need to use it in any of our calculations, we're choosing, in this particular case, we're choosing samples of size 3. If you let capital N be the population size of HTTC students, then it would be N combination 3 would be the total number of sample means that we would have here. The good news is we don't necessarily have to go ahead and construct this thing by hand, get all of the different sample means to eventually work out what its mean and standard deviation are going to be. There's a theorem that tells us this. And a couple properties of the sample distribution are as follows. The mean of the sample means, meaning the mean of this sampling distribution, is simply going to be equal to the population mean. So mu sub x bar, if you take all of those sample means, you add them all up, you divide by the total number of sample means that you have, that value is actually just equal to the mean of the original population. The standard deviation of the sampling distribution is also related to the standard deviation of the original distribution via the following relationship. Sigma sub x bar is equal to sigma, that would be the population standard deviation, divided by the square root of the sample size. Okay. Again, this is the standard deviation of our sampling distribution. It's also sometimes referred to as the standard error of the mean. So in this last section, these are 2 very, very important formulas that you want to kind of put to memory. We'll get a lot of practice with them in the next batch of examples. But mu sub x bar is simply equal to mu, and sigma sub x bar is equal to sigma divided by the square root of n. Let's take a look at example 1. Suppose we have a population that has a mean of 100 and a standard deviation of 15. Excuse me, we're going to find the mean and standard deviation of the sampling distribution of the sample means if we use a sample of size 20. Now keep in mind this information here, the starting information, this belongs to the original distribution. We now want to find the corresponding qualities for the sampling distribution. We know that mu sub x bar is always equal to mu, so if the mean is 100, the mean of the sampling distribution will also be 100. To find the standard deviation of the sampling distribution, we take the standard deviation of the population, which is 15. We're going to divide it by the square root of our sample size, which is 20. So we get 15 divided by the square root of 20, which is approximately 3.35 rounded to the nearest hundredth. A common question, and this will be asked quite a bit in the homework too, asks what happens to the standard error of the mean, or that sampling distribution standard deviation, when you change the size of the sample. For example, what if we change the sample size, instead of sampling 20 for each collection of the subset, what if we bump that up to 50? What would be the net overall effect? In other words, what happens to sigma sub x bar? Well, let's go back to our formula. We know sigma sub x bar is equal to sigma divided by the square root of n. Our sigma isn't changing, that's still part of the original population, that's 15, but we're now dividing it by the square root of 50, and what we get is 2.12. So essentially what happened, well, the sample size increased. We went from 20 to 50, and what we saw happen is that the standard error of the mean actually would decrease. So the moral of the story is when n increases, so as the sample size increases, the standard deviation of the sampling means gets smaller. Intuitively, one of the ways that you can kind of think about this is when your sample size increases, that means that each subset you're forming contains more of the elements that belong to the overall set itself, the original population, and therefore there's not going to be as much information left out. You're not going to get as much deviation from subset to subset as if you would if you're just sampling a few of them whenever you're doing your sampling distribution. But very important here, we have to know at the basic level how to compute mu sub x bar and sigma sub x bar. You should also know this kind of general overall pattern. As n increases, sigma sub x bar will always decrease. When we repeatedly take samples from a population and build a distribution of sample means, this distribution will be a normal distribution under certain conditions. And for us, this is going to be very important. From what we've learned previously in this chapter, from 5.1 through 5.3, if we have a normal distribution, then we know how to compute all kinds of probabilities and percentages if the distribution is normal. Well, the central limit theorem will tell us, as a result of this sampling process, exactly when we'll be able to guarantee a normal distribution. So the central limit theorem states as follows. If samples are drawn from a population with a mean equal to mu and a standard deviation equal to sigma, then the sampling distribution of sample means will be approximately normally distributed if one of these two things happens. First of all, if the sample size is large enough, for us that large enough benchmark is going to be 30 or more. So if n is greater than or equal to 30, then the sampling distribution will be normally distributed. Okay. Alternatively, if we know that the original population is normally distributed, then the sampling distribution itself will be normally distributed for any sample size. Okay. So one of two criteria, you have to have one of these two things being met. Obviously, if the original population is normal, then automatically your sample distribution will be normal regardless of the sample size. You can do samples of size 10, 5, 32, it doesn't matter. If the original is normal, the sampling distribution will be normal. On the other hand, if you don't know that the original population is normally distributed, then you would have to have a sample size of at least 30 or more in order to guarantee that the sampling distribution itself is going to be a normal distribution. The area where we get into trouble with is when people create small sample sizes that are less than 30, and the samples are taken from non-normally distributed sets. In that situation, the central limit theorem would not apply, and we wouldn't be able to guarantee that the distribution of samples would be normally distributed, and therefore we would not be able to do any kind of probability calculations as we did earlier in this chapter. There are advanced methods in statistics to kind of work around that, but we will not focus on those in our class. In either case, we can always talk about the mean and the standard deviation. Mu sub x bar, we saw this before, is equal to mu, and the sigma sub x bar is equal to sigma divided by the square root of n. If you want kind of a visual of what the central limit theorem is telling us, in case 1, let's suppose we have some kind of funky and odd distribution originally. So this is our original population. It's clearly not normally distributed. It's not bell-shaped curve. It's got almost kind of like bimodal thing going on here. It's maybe a little bit skewed to the right. But if you have a sample of size 30 or more, then notice that the sample distribution that's created from that, it in and of itself will be a normal distribution. In case 2, if we already start with a population that's normally distributed, then no matter what sample size you want to use, the sampling distribution will also be a normal distribution itself. Let's take a look at example 2. In example 2, they say that cellular phone bills for residents of a city have a mean of 64 and a standard deviation of 9, as shown in the graph. So we look at this graph. They tell us that it's a mean of 64, standard deviation of 9. We're going to randomly select samples of size 36, and from this we're going to create the sampling distribution. The first thing they want to do is find the mean of the sampling distribution. So we're looking for mu sub x bar. Remember, mu sub x bar is always the same thing as mu. If mu is 64, then mu sub x bar will also be 64. In part B, they want us to find the standard error of the mean of the sampling distribution. That's the mu sub x bar. We know that mu sub x bar is equal to sigma, which is 9, divided by the square root of n, which in this case we said was a sample of size 36. So it's going to be 9 divided by the square root of 36, which is 9 divided by 6, which is equal to 1.5. In part C, they ask us to now draw a sketch of the sampling distribution. One of the things, if you look at the original distribution, it looks roughly normal. So it looks like this might be a slightly rough normal distribution. But irregardless of that, notice that our sample is of size 36, which is certainly 30 or more. So that in and of itself guarantees that this sampling distribution is going to be a normal distribution. So when they ask us to sketch it, we want to make a nice bell-shaped curve. Our mean on this thing would be mu sub x bar, which would be 64. That's going to go right here. And then properly speaking, as we did in class, we really should be measuring off 3 standard deviations to the right, 3 standard deviations to the left, and the standard deviation you would use for this would be your sigma sub x bar. So you would want to add 1.5 to go to the right. So we'd have 64 as our mean, 65.5, 67, 68.5, and then you would want to subtract that standard deviation to go to the left. You would have 62.5, 61, and then I believe 59.5 would be the third on the left. In part D, asks what happens if we change the sample size to 100? Well, our sample originally was of size 36. If we're increasing it, then we know sigma sub x bar will go down, but let's just compute that to verify. Sigma sub x bar in this case is going to be the standard deviation divided by the square root of the sample size. That's going to be 9 divided by the square root of 100, which is going to work out to be 0.90. Okay. Comparing the two, with a sample size of size 36, it was 1.5. We increased the sample size to 100, and it went down to 0.90. So as sample size increases, the standard deviation of the sampling distribution decreases.